Your wall socket and your phone charger are actually speaking two completely different electrical languages, and your charger is secretly translating between them every single time you plug in. So why do we even need two types of electricity in the first place? Well, those two languages have names. The electricity coming out of your wall is called alternating current, AC, and the electricity stored inside your phone, your laptop, your TV remote, your car battery, that's called direct current, DC. Now, these two aren't just slightly different versions of the same thing. They behave in completely opposite ways. They were invented by rival scientists. They sparked one of the most dramatic and ruthless battles in the history of technology. And today, in the 21st century, both of them are more important than ever. By the end of this video, you'll understand exactly what AC and DC are, why they work differently, how a bitter war between two geniuses shaped the entire modern world, and why your phone charger is honestly one of the most underrated pieces of technology you own. All right, let's start with the simpler one, direct current, or DC. Imagine electricity as water flowing through a pipe. In direct current, the water, or in our case the electrons, always moves in one direction, from the negative end of a battery, through the circuit, to the positive end. Straight, steady, and consistent. It never changes direction. It never reverses. It just flows. And that consistency is actually really useful, because when you're powering a small device, a phone, a laptop, a flashlight, you want a smooth, stable supply of power. You don't want the electricity to suddenly reverse direction while your phone is trying to save a file. DC is also what comes out of every battery ever made. That AA battery in your TV remote, DC. The giant lithium-ion battery pack in a Tesla electric car, DC. Solar panels on a rooftop, they generate DC. It's the natural output of chemical energy being converted to electrical energy. Direct current was also the very first type of electricity to be commercially used at large scale, and the man behind it was one of the most famous inventors in history, Thomas Edison. In the 1880s, Edison built the world's first power stations in New York City, pumping DC electricity into homes, businesses, and street lamps. It was revolutionary. It was groundbreaking. People had never experienced anything like it. But DC had one enormous fundamental problem, and that problem would eventually cost Edison everything. DC voltage drops dramatically over distance. The further electricity has to travel through a wire, the more energy it loses as heat. With DC technology available at the time, you could only send power a mile or two before it became too weak to be useful. That meant Edison needed to build a new power station every mile or so across every city he wanted to power. That's not just expensive. That's practically impossible at national scale. Edison knew this was a problem, but he didn't have a good solution. And while he was trying to figure it out, a young immigrant, Nikola Tesla, arrived in America with a bold new vision of alternating current, one that would change everything. Let's dive in and understand what alternating current really is. In alternating current, the electrons don't flow steadily in one direction. Instead, they rapidly oscillate. They move forward, then backward, then forward again, switching directions many times per second. In the United States, AC switches direction 60 times per second. In Asia, Europe, and most of the rest of the world, it's 50 times per second. That number is called the frequency, and it's measured in a unit called hertz. Now, your brain is probably asking the obvious question. If the electrons are just going back and forth and not actually traveling anywhere, how does electricity even get from the power station to your house? Here's the key insight. The electrons themselves don't need to travel. What travels is the energy, the push. Think of it like a slinky. If you push one end of a slinky, you don't need the coils on one end to physically travel to the other end. The energy travels as a wave through the whole thing almost instantly. Your wall socket isn't sending electrons from the power plant to you. It's sending a wave of electrical energy that pushes the electrons already inside your home's wiring back and forth. And that movement is what powers your devices. Pretty wild, right? Now here's the real reason AC won the future. And it comes down to one incredible device called the transformer. A transformer can take AC electricity at 1 voltage and convert it to a completely different voltage, higher or lower, with very little energy loss. And that capability is absolutely game-changing. Here's why. When you want to send electricity over long distances, you want to do it at very high voltage and low current. Because power loss in a wire equals current squared times resistance. The lower the current, the dramatically less energy you waste as heat. Transformers make it easy to step AC voltage way up for long-distance travel. Then step it back down to safe levels when it reaches your home. With DC in Edison's time, stepping voltage up and down efficiently was essentially impossible. With AC and transformers, you could send power hundreds of miles with minimal loss, then bring it down to household voltage at the other end. That's the technical reason AC took over. But the human story of how it actually happened. And this is where things get really interesting. The year is 1887. Thomas Edison is the most famous inventor in the world. He has money, fame, investors, and a DC electrical empire he has spent years building. And then, a young Serbian-American engineer named Nikola Tesla, who had actually worked for Edison briefly, starts publicly promoting an AC electrical system backed by a wealthy businessman named George Westinghouse. Edison immediately understood what was at stake. If AC succeeded, his entire DC infrastructure would become obsolete overnight. Hence, he launched a campaign, which historians now call the War of Currents, a public relations campaign designed to convince the American public that AC electricity was terrifyingly dangerous, and DC was the safe, responsible choice. But physics doesn't care about public opinion. In 1893, Tesla and Westinghouse lit up the entire Chicago World's Fair, 100,000 light bulbs on AC power. The crowd was speechless. 2 years later, they harnessed Niagara Falls and sent electricity 20 miles to Buffalo, New York. DC was finished, but their battle, as dramatic and ugly as it was, gave us the electrical grid that powers the entire modern world. So that was the 19th century. What does the AC versus DC picture look like today? Here's the fascinating twist that almost nobody talks about. DC is making a massive comeback. Think about the major technological trends of the 21st century. Solar panels generate DC electricity. Wind turbines often produce variable AC that gets converted to DC and back. Electric vehicle batteries store DC. Smartphones, laptops, tablets, smart home devices, all DC. And massive data centers, which now consume a significant percentage of global electricity, are increasingly switching to DC power distribution internally because it's more efficient for their hardware. And then there's something called high-voltage direct current transmission, HVDC. Remember how Edison's DC couldn't travel long distances? Modern power electronics have completely solved that problem. HVDC cables can now transmit DC power thousands of miles with even less loss than AC lines. There are HVDC cables running under the North Sea connecting the power grids of different countries. There are HVDC lines crossing entire continents. Even your charger, that little block you plug into the wall, is actually a surprisingly sophisticated gadget. 120 or 230 volts of oscillating AC enters your charger. A tiny but incredibly engineered circuit converts it into smooth, stable DC. Your phone battery stores it, and tomorrow morning, that stored DC energy powers a device containing billions of transistors, each one operating on voltages your charger measured to within fractions of a volt. You've been carrying around a miniature power conversion system in your bag this whole time without even thinking about it. So, the world today doesn't run on AC or DC. It runs on both, in a constant, invisible collaboration. AC comes from the power grid into your home. Your devices convert it to DC. Your solar panels generate DC that gets converted to AC to feed back into the grid. Your EV charges on AC but stores DC. It's a beautifully complex dance between two systems that were once bitter rivals. Edison wanted a DC world. Tesla wanted an AC world. The future turned out to need both of them, and perhaps that's the most fitting ending to their story. So, let's bring it all together. Direct current flows in one direction. It's stable, predictable, and perfect for electronics, batteries, and devices that need clean, consistent power. It was Edison's vision. And while he lost the war of currents, his vision lives on in every battery, every solar panel, and every electric car on the road today. Alternating current oscillates back and forth. It's incredibly efficient for long-distance transmission thanks to transformers, and it's what powers the grid that supplies electricity to virtually every building on Earth. It was Tesla's triumph, and it remains the backbone of global energy infrastructure. Two very different systems. Two very different inventors. One world that needed both of them. If you enjoyed this video, please hit the like button. It genuinely helps more people discover this content. Subscribe if you want more videos that dig into the science and history behind the technology we use every day. And drop a comment below. Team Edison or Team Tesla? I read every single one. I'll see you in the next one. Stay curious.